All right, 6.3, interpreting the rate of change of exponential models. So objective, given a function, you guys like my lightsaber pointer, students will be able to find the factor by the quantity per unit time interval and vice versa. So that means we're looking for a change over a certain amount of time. You're going to hear me refer to that as one change. We're going to think, a lot of times we're going to be able to solve these problems by just thinking about how long does it take for one change to occur. And I'll explain that as we do a couple examples. So what I have here is the standard form of an exponential function. And so here's our function. And usually with these things, we're going to use t instead of x. That's because we're talking about time. See, t, this represents time in some units like days, hours, or years. And notice that our variable is up here in the exponent. That's what makes it an exponential function. So we have p, this is our principal amount or starting amount, times 1 plus r. R is our rate. This is the rate of change. It's entered as a decimal, but in word problems, it's often discussed as a percentage. So like, let's say it was increasing by 10%. We wouldn't write 10% here, we'd write 0.1. T, like we already discussed, is our time interval. A, this is the amount of time in the same units as t it takes for one change to occur. So it's kind of counterintuitive because you divide by it. But basically, let's say it took 5 seconds for something to double. That means that A would be 5 and we write T over A. We'll play with this a little bit so you can kind of get an exact idea of what's going on here, but I think you'll catch on relatively quickly here. And a lot of times this A value here is actually just 1. I think that's the case in this first problem we're going to do. So it's just, the t just looks like, t divided by 1 is just t. So you don't even see that a value, but it's important to know that we can divide it by a if we have a problem where that's something different than 1. Okay, so let's take a look at this first problem. Okay, it says, Mr. Price uploaded a funny video on his website, which rapidly gains views over time. The relationship between the elapsed time t in days since he uploaded the video. So t is in days. That might be important to highlight or something, right? T is in days. Since he uploaded the video and the total number of views, v of t is modeled by the following function. So here, this means total number of views, and we have this function here. And so we could actually interpret what's going on here. We can see based on this little chart up here, we could see what these numbers mean. So like, for example, how many views did his video have on the first day? Well, we were told that the p-value, or the starting value, it is the starting value, sorry. So the p-value is the starting value. So how many views did he have on the first day? Well, it says right there he had 100 views. And then the next question says, are the views being added to or subtracted from each day? Well, this number here is greater than 1, right? This 1.65 is greater than 1. We said that right here. If it's positive, then the function represents growth. If it's negative, then the function represents decay. Well, think about that. If r is some positive value, then 1 plus r will be greater than 1. And if r is negative, then 1 minus r would be less than 1. Well, this is greater than 1, so we know that it's being added to. Added to each day. Okay, what is the percent at which these videos are changing each day? So this goes into that one change thing, right? It looks like it's changing each day. That's why our t value is 1 here. We could kind of zoom in, and technically this equation could be written as t divided by 1 because it's gaining a percentage every 1 day. But you're going to see problems where it gains a percentage every 2.5 days or every 5 days or every 30 seconds or whatever. And so then you're going to have to do t over that number. But this is just over 1 day. And it looks like our r, if we were to kind of dissect this, right, this before we started was 1 plus 0.65. If we want to think about it in terms of how we wrote this original equation, right, that's 1 plus 0.65, so that our r is 0.65. And we already discussed how our r is the rate of change. It's entered as a decimal, but often discussed in word problems as a percentage. So what is the percent at which these views are changing each day? Well, instead of 0.65, we would write 65%. It's growing by 65% each day. And that's actually a good idea for us to say that it's growing by 65. There we go. Now we can say it's growing by 65% each day. All right, and the last question says, what if the function was v of t equals 500 times 1.110? What would be different? Well, we could kind of tell what would be different. First of all, the starting value is 500 now instead of 100. So I just put that in there in the text box. Starting value is 500 instead of 100. And also, we can look at this value inside here. We could see that it's not growing by 65%. Looks like it's going to be growing by 10%. So we could add that as well. Okay, so I typed in the answer instead of writing it all in. I thought maybe that would be easier to see. But starting value is 500 instead of 100, because I have a 500 instead of 100. And starting value is 10% instead of 65, because I have a 10 instead of a 0.65. So hopefully we could see that. All right, so that's a good example problem. I got another one for you guys to try on your own, but let's read it together here in practice one. Miss Roush began studying a sample of the chemical element known as Einsteinium-253. I don't think that's a real chemical, but for the sake of this problem, it works. Which naturally loses its mass over time. Okay, that seems like that could be important. It loses its mass over time. The relationship between the elapsed time t in days, so t is in days again, since she started studying the sample, and the total mass remaining in the sample, Emma T in micrograms, is modeled by the following function. Okay, we got our function here, and we could see a couple things. We could see our starting value, and we could see that this value is less than 1. That's important. That's why it's losing its mass over time, because if you go back up to the regular thing, we said here, if it's negative, then the function represents decay. That was in reference to this R value, right? And if this is negative, we can tell that 1 is going to be 1 minus some number, and so that's why we get a value less than 1. So it turns out we can actually see what we had before this thing started. Let's play with this idea. Remember that this 0.93 in here was 1 plus some R value. So you could think of that as 1 plus a negative 0.07. That's how they got to this 0.93. You really have to be able to kind of see where that came from in order to answer a lot of the questions in this problem. Okay. So let's continue. It says, what was the mass when Miss Roush started studying the sample? That's easy. That's just this number out in front. You guys should be able to do that part. Part B is the mass being added to or subtracted from. We talked about that when we looked at the equation. We looked at the standard form. And part C, what is the percent at which the mass is changing each day? Okay, I think that you guys can do all this. I've kind of broken down the problem for you, but just give it a try. And then pause the video and check your answers when you're done. All right, so we can see right away that the mass was 159 micrograms because that's our principal value, our p-value out in front, so that's pretty easy. Is the mass being added to or subtracted from? This number inside the parentheses is less than 1, and our r is negative, therefore it is being subtracted from. What is the percent in which the mass is changing each day? We kind of did this together when I told you to think about this as 1 plus r, and we found out that r would have to be negative in order to get to 0.93. So we can see that it's losing 7% each day. That's what that negative 0.07 represents. That's losing 7%. Okay, let's go on to the next page. All right, so let's look at example number 2 here. It says, after a special medicine introduced into a petri dish containing a bacterial culture, the number of bacteria remaining in the dish decreases rapidly. That sounds important, decreases. The relationship between the elapsed time t in seconds and the number of bacteria in a t in the petri dish is modeled by the following function. Okay, so now we have something a little bit more complicated going on here. N of t equals 5,000 times 3 over 7, t divided by 6. See, so we have an a value of 6 here. That's important. We'll talk about what that means. The bacterial culture loses 4/7 of its size every what? Okay. Let's dive in. Let's talk about this. First of all, kind of different. They have this as a fraction, but let's think about this 3/7. Let's kind of play with this number here. I'm going to just kind of highlight it, and we'll talk about it off to the side. Remember that that number inside parentheses has to equal 1 plus some R value. And so we can actually solve for what our R value is. It's just simple algebra, right? You're going to subtract 1. And so we could say that R would equal 3/7 minus 1. But instead of putting minus 1 there, I'm going to put 7 over 7. Okay. Well, 3 minus 7, that's -4. So we got -4/7. Okay, so our R is -4/7. Now, that's why it says that it loses 4/7 of its size. Okay, so this is representing that one change right here. This is 1 minus 4/7. That's how they got this part, because it's losing 4/7. So that's important to recognize how these numbers are related, okay? They did a little bit of math already here, and they got these numbers. So now, how often is that happening? Well, remember, we said that the A value is the time it takes for one change to occur. And so we actually can just kind of look at this and see what the answer is. But I want to explain another way of thinking about it. In order for one change to occur, this exponent here, this exponent would have to equal 1. Okay, so whatever you plugged into t, it'd have to equal 1 so that we would just have one change here, right? Because we want 5,000 times one change. If it was anything other than 1, we would have multiple changes occur. Or maybe not a full change, but if this exponent is 1, we get one full change. Well, now that's a pretty easy equation to solve. T over 6 equals 1. You can just multiply both sides by 6. And the time it takes then for one change to occur is 6, or 6 seconds in this situation. But we kind of already answered that, because we said on the previous page that the A value, whatever is the number that it's divided by, is the time it takes for one change to occur. And since we already know that one change is losing 4/7, then we know that 6 seconds has to be the answer here. So this concept of one change occurring, we'll see that, we'll play with that a lot more in future problems. Okay, we got another problem here. This one's a practice problem. I'm going to read it through with you guys, get you guys started. But it says, Mr. Busher started studying how the number of branches on his tree grows over time. The relationship between the elapsed time t in years since he started studying the tree and the number of its branches, n of t, is modeled by the following function. So we have our function here. And it says the number of branches quadruples every how many years? Okay, quadruples. What does that mean? Well, to quadruple means that it's going to multiply by 4 every year. Well, and it's not every year, sorry. It's every how many years. So we got to look at this problem to dissect that and figure out how many years does it take for it to multiply by 4. Well, hopefully you could just quickly tell just by looking at this. So go ahead and unpause the video when you're ready to check your work. So hopefully you just saw, that your A value is 12. That means that it takes 12, in this situation, 12 years, because t is in years, for one change to occur, and that one change is being multiplied by 4. So the number of branches quadruples every 12 years. Now I want to show you an example of a slightly higher problem. Let's say we did the exact same problem, and we can call that problem example number 3. But let's say I was asking about the number of branches doubles every how many years? What if I asked for doubles and we use all the same information up here? Well, let us think about how we could get that to look like it doubling, because right now it's being multiplied by 4. It's not being multiplied by 2, but we can actually change the way this looks. So let's play with it. We know that we have n of t equals 19 times, and I'm going to put something that's equal to 4 there, t over 12. Well, if I wanted it to double, I could think of it as 2 squared. There, now I have a 2, so now it will be doubling, but now I'm going to have to simplify this thing out just a little bit. So I got equals 19 times 2, and this little 2 here, this little 2 in the exponent, we've learned that if you have an exponent inside the parentheses and an exponent outside the parentheses, you could just multiply these. And so we could say this is like 2t over 12, which of course we could reduce that. So we could write this equation as 19 times 2t over 6. And so now if I was asking how long it took for it to double, we could see, hey, that's t over 6. My a value now is 6. And so we could say, hey, it would take 6 years for it to double, which makes sense. If it takes 12 years for it to quadruple, it should take 6 years for it to double. Just another way that you could manipulate the formula, just showing you how you can manipulate the formula to get to the information they're asking about, just in case they ask for something a little bit more complicated. All right, that's it for this video. I'll see you guys on the next one.